As a sub goes out on patrol and prepares for its initial dive, many thoughts must enter the minds of the crew. I wonder how long we'll be gone. At what depth will we be operating? How well did they put this ship together anyway? Did that welder who welded the hull really know what he was doing? Maybe this sailor has a reason to be concerned. For as a submarine dives, water pressure on the hull builds up at a rate of nearly 1/2 pound for every foot down it goes. For example, if the sub dives to 400 feet below the surface, there is approximately 178 pounds pressure on the hull. The hull must stand up to this pressure. In addition to diving pressures, the hull must also withstand depth charge attacks, explosions, and near misses. The welds you make on surface ships are equally important. These welds must also be able to withstand great stresses from such forces as heavy seas and combat action. All this brings us to the point where ships are constructed. Quality welds begin here. The welders employed at a shipyard are highly skilled. Like you, they must pass rigid examinations before they can weld on ships. And their welds are subjected to the same rigid standards yours are. Navy welding standards must be extremely rigid. There's no room for second best. How then do we get high quality welds? Let's see what happens when the arc strikes. The temperature of the arc, when manual metal arc or MMA welding, is approximately 6,500 degrees Fahrenheit, which is more than sufficient to melt the base metals and electrode. While the metals are in a liquid state, they mix with filler material from the electrode, which is added to the puddle. In these views of the arc and puddle, we have considerably slowed down puddle action and increased image size to show you what actually is taking place in the puddle. You can see liquid metal boiling and giving off gases. Notice how the base metal melts at the leading edge and sides of the puddle. Note the continual movement of the arc. You can see the metal and flux transferring from the electrode to the puddle. You can see flux floating on the surface to protect the puddle. The flux also slows the rate of cooling somewhat and allows the weldment to temper slightly. Here, as the action is once again speeded up, you can see how manipulating the electrode affects the puddle movement. The other two arc welding processes, which we'll cover in more detail, are called tungsten inert gas, or TIG, and metal inert gas, or MIG. Metals such as stainless steel, Monel, Inconel, and copper nickel, all of which go into the makeup of nuclear power plant piping systems, are also easily MMA welded. Here, the welded systems must withstand both high temperatures and extremely high pressures. MMA welding makes the construction and repair of these exotic systems quite easy for the skilled welder. The heart of the modern warship is its power plant. The boilers, engines, and related components in use today are designed to operate with extremely high temperatures and pressures. The piping systems are constructed of metals such as carbon molybdenum and chromium molybdenum steel alloy, and are MMA welded. Without the ease of MMA welding, it would be nearly impossible to construct and maintain these power plants. The hulls of modern Navy ships are completely welded when constructed. Some ships might qualify as the largest all-welded construction in existence. The MMA process has greatly contributed to this, since a large percentage of welding is done with this process, and these welds can stand up to anything the base metals can. TIG welding differs from MMA welding in that the electrode does not melt, and the arc and molten puddle are protected from the atmosphere by an inert gas, usually argon or helium, or a mixture of argon and helium. TIG welding may be performed using no filler metal, as the welder is doing here. In this instance, the edges of the two base plates are simply melted and fused together. When welding carbon steel, the puddle is quiet and easily controlled. The inert gas flows out of the torch through a ceramic cup that surrounds the tungsten electrode. The electrode is made of tungsten because we don't want it to melt, and tungsten has a very high melting point. As you view the puddle action, notice how the base metal melts at the leading edge of the puddle. Observe the solidification rate of the puddle at its trailing edge. This puddle action is very characteristic of carbon steel being TIG welded. Other applications may require that additional metal be added to the puddle. This is accomplished by using a filler rod. Here, two stainless steel plates are being welded using a filler rod. Especially note that the filler rod melts before touching the puddle. Observe the oxides floating on the puddle. In some cases, an insert is placed between two pieces of specially machined pipe. The insert takes the place of a filler rod. The insert and the adjoining pipes are melted and joined by the arc from the TIG torch. Watch the insert melting and mixing with the base metal as it appears inside the pipe. The inside of the pipe must be kept inerted during this process. Usually an inert gas is maintained inside the assembly. Other than the insert, no additional filler metal is added at this point. The insert, when it is completely pulled, makes up the first layer or root layer of the welded joint. One of the biggest advantages in using the insert and the TIG process in pipe joints is that it provides a smooth interior to the joint inside of the pipe, and thus creates less restriction to the flow of liquids. Here, the welder is allowing his arc to decay, thus permitting the puddle to cool and solidify. Let's look at some other common uses of TIG welding. Many shipboard piping systems are now made of copper nickel and are entirely TIG welded. Sheet metal welding uses the TIG process to a large degree. There is little danger of melting through the base metals because the arc and the puddle are so easily controlled. Metals thin as common aluminum foil can be TIG welded. In this instance, the welder is joining two pieces of 5/1000ths of an inch Inconel using a lap joint and no filler metal. We get a good strong joint in metals even this thin with the TIG process. The third welding process, MIG welding, is kind of a cross between MMA and TIG welding. The arc and puddle are surrounded by an inert gas, argon or helium, or a mixture of argon and helium, as in TIG welding, while the electrode is melted and added to the puddle as filler metal, like in MMA welding. The MIG filler metal comes in rolls of wire. This wire is fed through a gun automatically when the welder presses the gun's trigger. As you watch the puddle action of aluminum being MIG welded, observe the rhythm with which the globules of filler metal strike the puddle. Notice how waves are created in the puddle and how the puddle melts the base metal at the leading edge. Again, you see surface oxides floating on the puddle. Notice also that there has been no color change in the base metal, normally seen with other welding processes and metals. Let's look at some common uses of MIG welding. MIG welding is used extensively in constructing ships such as minesweepers and patrol craft. This is because the hulls are constructed entirely of aluminum. In addition, MIG welding is used on the aluminum superstructures of modern ships. MIG welding is readily adaptable to metals other than aluminum. For example, the MIG process is used extensively to weld ships' hulls constructed of steel alloys. To conclude this introduction to arc welding, the three types in common shipboard use today are MIG, TIG, and MMA. MMA, the most widely used because it is the most economical and can be used in a large variety of metals, uses an arc with a temperature of approximately 6,500 degrees Fahrenheit to melt the base metals and electrode. While the base metals and filler material from the electrode are in a liquid state, they mix. The flux from the electrode protects the base metals from impurities. After the weldment cools, the weld is as strong as the original base metal. TIG welding differs from MMA in that the electrode does not melt. Filler material may be added to the puddle using a filler rod, and the puddle is protected from the atmosphere by an inert gas. Finally, MIG welding, widely used for welding aluminum, is a cross between MMA and TIG. The electrode is consumed in the puddle, while the arc and the puddle are protected by an inert gas. One final note. As man goes to deeper depths in the ocean, he becomes increasingly more dependent on metal enclosures to protect him, and metal enclosures require high-quality welds. There is no room for second-best welding when life itself depends on quality welds.